It started to sink in that we may be experiencing something that's abnormal on the spacecraft.
For decades, Pluto was dismissed as a frozen, lifeless rock drifting through the outer solar system.
Even though logically I knew that it was a rocky, icy planet, I didn't expect it to look so similar to features that we have on Earth.
Too small, too cold, and too far from the sun to support any kind of activity, let alone life. Even after NASA's New Horizons flyby in 2015 revealed a surprisingly dynamic world, most scientists believed Pluto was still a dead planet.
Pluto is geologically alive after 4.5 billion years, which upended many geophysical theories.
Just one with an interesting geological past. Then came the James Webb Space Telescope. When it turned its infrared gaze toward Pluto, researchers expected to see a familiar, frozen landscape. Instead, they found something shocking: strange heat signatures, unusual atmospheric changes, signs of complex organic molecules. Suddenly, everything we thought we knew about Pluto was in question. If a world like Pluto can defy expectations, what does that mean for life in the universe? The answer might be more unsettling and more exciting than we ever imagined. Pluto's mysterious heart, more than just ice. For decades, Pluto was seen as a frozen, inactive rock at the edge of the solar system, but that changed when NASA's New Horizons spacecraft sent back detailed images in 2015. One of the most striking features on its surface was a massive, heart-shaped region known as Sputnik Planitia. This enormous glacier, covering more than 1 million square miles, immediately stood out, not just for its distinctive shape, but for its unusual properties. Unlike other icy landscapes in the solar system, Sputnik Planitia appears to be geologically young, with no visible impact craters. That suggests something is reshaping the surface, challenging the long-held assumption that Pluto is a dead world. But the real mystery lies beneath. Scientists now suspect that under its frozen crust, Pluto might be hiding something completely unexpected, a vast underground ocean. When New Horizons flew past Pluto in 2015, one of its most iconic discoveries was Sputnik Planitia, the bright, heart-shaped feature stretching across the dwarf planet's surface. Measuring roughly 1,000 miles across, this icy plain is composed primarily of solid nitrogen, along with carbon monoxide and methane ice. Its striking appearance quickly made it one of the most recognizable planetary features in the solar system. But its true significance goes beyond its looks. Most of Pluto's surface is heavily cratered, a sign that it has remained geologically unchanged for billions of years. But Sputnik Planitia is completely smooth, with no visible craters. That means something is actively reshaping the ice, erasing evidence of impacts over time. This is incredibly unusual. On an airless, frozen world like Pluto, scientists expected to find a static landscape, not one that appears to be constantly renewing itself. One explanation for this strange phenomenon is that Sputnik Planitia is a convection-driven glacier. The nitrogen ice is believed to be cycling like a lava lamp, with heat from Pluto's interior causing chunks of ice to slowly rise and sink over time. This process would naturally erase craters and keep the surface looking fresh. But where is that heat coming from? And could it point to something even more surprising? The discovery of Sputnik Planitia's apparent activity led scientists to a startling hypothesis. Pluto might have a subsurface ocean. When New Horizons mapped Pluto's gravity field, researchers noticed something odd. Sputnik Planitia sits directly opposite Charon, Pluto's largest moon. This is likely not a coincidence. The vast glacier appears to have caused Pluto to tip over, aligning itself with Charon's gravitational pull. This suggests that Sputnik Planitia is unusually dense, which is strange considering that nitrogen ice is relatively light. The best explanation: there could be a massive underground ocean beneath it, made of liquid water mixed with ammonia or other antifreeze-like compounds. If such an ocean exists, it leads to a huge question. How has it remained liquid? Pluto is located nearly 4 billion miles from the Sun, with surface temperatures dropping to negative 400 degrees Fahrenheit. Under normal conditions, any water should be completely frozen. Yet the evidence suggests that heat from Pluto's core, along with the insulating effects of an icy crust, may have been enough to keep the ocean from freezing solid for billions of years. Even more surprising, this hidden ocean may not be entirely isolated. Cracks and fractures seen across Pluto's surface suggest that water or slushy ice could occasionally erupt onto the surface, similar to what happens on Saturn's moon Enceladus. If true, Pluto isn't just an icy rock, it's an active world with internal processes reshaping it from the inside out. If Pluto has a liquid ocean beneath its icy crust, it leads to an incredible possibility. Could something be living in it? Scientists have long believed that the best places to look for life beyond Earth are in subsurface oceans, where liquid water is protected from harsh surface conditions. Moons like Europa and Enceladus are considered prime candidates because of their hidden oceans, but Pluto was never part of that conversation until now. If Pluto's ocean contains the right chemical ingredients, microbial life could theoretically exist there, just as life thrives in deep-sea hydrothermal vents on Earth. The presence of complex organic molecules on Pluto's surface, detected by both New Horizons and the James Webb Space Telescope, adds another intriguing layer. These molecules, which include hydrocarbons and nitrogen compounds, are the building blocks of life. If they are mixing with the subsurface ocean, Pluto could have the raw materials needed for biological processes. Astrobiologists speculate that if life exists on Pluto, it would likely be simple, extremophile microbes, similar to those found in Earth's most extreme environments. Deep beneath Antarctica's ice sheets, microorganisms have been discovered thriving in subglacial lakes, cut off from the rest of the world for millions of years. Could something similar be happening on Pluto? The geology that shouldn't exist. When scientists first examined Pluto's surface in detail, they expected a world shaped by billions of years of cosmic collisions, frozen solid in the deep cold of space. Instead, they found a dynamic landscape that seemed impossible for such a small, distant world. Towering mountains made of solid ice, vast plains that appear to be in motion, and a surface that looks unexpectedly young all point to geological activity, something Pluto was never supposed to have. How can a dwarf planet with no volcanic eruptions or plate tectonics still be reshaping itself? The answer might lie deep within Pluto, where lingering heat and complex internal processes could be driving one of the most surprising geological stories in the solar system. One of the most striking discoveries made by NASA's New Horizons mission was Pluto's mountains, some reaching over 4 miles high, comparable to the Rocky Mountains or the Alps on Earth. But unlike Earth's mountains, these are not made of rock. Instead, they are composed of solid water ice, a material so rigid at Pluto's frigid temperatures that it behaves like stone. How did these mountains form? With no evidence of active plate tectonics, Pluto lacks the forces that push up mountain ranges on Earth. Yet the presence of such towering peaks suggests that Pluto has experienced significant geological upheaval, likely caused by internal forces reshaping its surface over time. Some theories suggest that cryovolcanism, a process where icy material erupts instead of molten rock, could be at work. While Pluto's atmosphere is too thin for wind erosion to carve these mountains, slow internal shifts could be pushing these icy peaks upward. But without a strong heat source like the sun or internal friction from a large planetary core, what is fueling this activity? Beyond its mountains, Pluto's surface holds even more perplexing features. One of the most baffling is Sputnik Planitia, the massive glacier-filled basin that forms the left side of Pluto's heart. This area, stretching over 1,000 miles, is strikingly smooth, completely free of impact craters. In the solar system, most celestial bodies, whether moons, planets, or asteroids, are covered in craters, the scars of billions of years of asteroid impacts. The fact that Sputnik Planitia lacks craters suggests that its surface is constantly renewing itself, as if Pluto has some unseen force smoothing it out. One clue comes from the unusual polygonal patterns found in Sputnik Planitia. These enormous cell-like shapes, some spanning 20 to 30 miles across, resemble patterns seen in lava lamps or boiling water. Scientists believe they are evidence of convection currents within the nitrogen ice. Much like Earth's mantle moves due to heat from below, Pluto's nitrogen-rich surface appears to be slowly churning, with warmer ice rising and colder ice sinking. This kind of activity should not be possible without an internal heat source, but where is Pluto getting the energy to sustain it? For Pluto to sustain active geology, it needs some source of internal heat, an especially difficult problem for a world so far from the Sun. Pluto should be completely frozen solid, but evidence suggests something is keeping parts of its interior warm enough for movement. One of the most plausible explanations is radioactive decay within Pluto's core. When Pluto formed about 4.5 billion years ago, it likely contained radioactive elements like uranium and potassium. Over time, these elements decay, releasing small amounts of heat. While this energy is nowhere near as intense as the heat generated by Earth's core, it could be just enough to prevent Pluto from freezing solid all the way through. This slow trickle of heat could allow a subsurface ocean to remain liquid beneath Sputnik Planitia. The water, insulated by a thick crust of ice, would slowly leak heat upward, causing the nitrogen-rich surface to move and convect, explaining the patterns observed on Pluto's plains. If this process is still happening today, it means Pluto is far more geologically active than anyone imagined. It also leads to a stunning possibility. If a small, icy world like Pluto can retain internal warmth and possibly sustain liquid water for billions of years, what does that mean for other distant frozen planets and moons? But there's a lot more to it than first meets the eye. Pluto's shifting axis, the influence of Charon. Pluto's position in the solar system has always made it an outsider, but its rotation and gravitational interactions make it even more peculiar. Unlike most planets, which spin in a relatively stable way, Pluto's axis has shifted dramatically over time. This means that its poles and equator have changed locations, a process known as true polar wander. But what caused this shift? Scientists suspect that Pluto's most distinctive feature, Sputnik Planitia, may be the key. The immense weight of its nitrogen glacier, stretching over 1 million square miles, could have caused Pluto to reorient itself, shifting the entire planet's spin. However, Pluto doesn't move alone. Locked in a unique gravitational dance with its largest moon, Charon, Pluto's movements are deeply connected to its cosmic partner. Pluto doesn't rotate like Earth. Instead of having a relatively upright axis, Pluto is tilted over 120 degrees, meaning it essentially spins on its side. This extreme tilt gives Pluto long, bizarre seasons, where one hemisphere experiences decades of continuous sunlight, while the other remains in total darkness. Adding to the mystery, Pluto's axis seems to have shifted over time, meaning that its spin was once oriented differently. Scientists believe this may be due to Sputnik Planitia's massive weight. The thick nitrogen ice in this region is so dense that it may have caused Pluto's crust to readjust, pulling the planet's entire orientation into a new position. This is a process called true polar wander, where a planet's outer shell moves over its core, causing its poles to shift. If Sputnik Planitia was once located somewhere else on Pluto, its current placement suggests that the planet's surface has repositioned itself, hinting at unexpected internal dynamics. But Pluto isn't just influenced by its own weight, it's also heavily shaped by its closest companion. Unlike most planetary systems, where moons orbit their parent planet in a clear hierarchy, Pluto and Charon behave like a binary system. Charon is so large compared to Pluto, about half its size, that instead of orbiting around Pluto's center, both bodies orbit a common point in space, almost like two planets locked in a gravitational embrace. This gravitational tug-of-war affects Pluto's rotation, surface stress, and even its internal heat distribution. Charon's influence could be responsible for some of the fault lines and fractures observed on Pluto's surface, where tidal forces stretch and compress the planet's icy shell. Scientists believe this interaction also plays a role in keeping Pluto's subsurface ocean from freezing solid. As Charon tugs on Pluto's interior, it may create enough internal stress to generate heat, similar to how Jupiter's moon Europa stays warm beneath its icy crust. One of the strongest pieces of evidence for Pluto's hidden ocean is the presence of long, deep fractures across its surface. These cracks, some stretching for hundreds of miles, suggest that Pluto's outer shell is experiencing stress from below. Similar patterns have been observed on Europa and Enceladus, two moons that are suspected to harbor subsurface oceans. On these moons, surface fractures are caused by the shifting of an underground liquid ocean pressing against the icy crust. If Pluto's cracks formed the same way, it strongly suggests that liquid water still exists beneath its frozen surface. Pluto's shifting axis, its relationship with Charon, and the evidence of ongoing geological activity point to something remarkable. Could life exist on Pluto? If Pluto has a subsurface ocean, as evidence increasingly suggests, then the next question is whether it could support some form of life. Astrobiologists have long searched for liquid water beyond Earth, considering it a key ingredient for life. Planets and moons like Europa, Enceladus, and even Mars have drawn attention because they may have, or once had, liquid water. Pluto's potential underground ocean now places it on the list of intriguing places to explore for life. But what kind of life could exist in such an extreme environment? And how would scientists even detect it? Renowned physicist Brian Cox has publicly entertained the possibility that Pluto might support life. In interviews and documentaries, he has discussed how a subsurface ocean, shielded from the harsh environment above, could provide a stable environment for microbial organisms. If life on Earth can thrive in the darkest, most extreme environments, then perhaps something similar could exist beneath Pluto's icy shell. The key question is whether Pluto's ocean, if confirmed, could remain liquid for billions of years, long enough for life to develop. Some planetary scientists believe that radioactive decay in Pluto's core, combined with the insulating effect of its ice shell, could generate enough heat to sustain liquid water. If true, this would mean that Pluto has defied expectations, maintaining conditions that might allow microbial life to survive. Even if Pluto has liquid water, it remains an incredibly harsh environment. The surface temperature averages around -375 degrees Fahrenheit, and even deep underground, conditions would still be brutally cold. This leads to several key challenges for life. Cosmic radiation is a major issue, as Pluto's thin atmosphere provides little protection from space radiation, which could be harmful to life. However, an underground ocean could be shielded from this radiation, which is a safer environment for microbes. Another issue is the lack of an obvious energy source. Life on Earth relies on the sun, but Pluto is so distant that sunlight provides almost no warmth. Instead, life would need to survive using chemical energy sources, similar to deep-sea organisms on Earth that rely on hydrothermal vents. The extreme cold and pressure would also slow biological processes drastically. Any life on Pluto would need to be extremely resilient, capable of surviving in near-frozen water with very limited energy availability. Despite these challenges, scientists have found organisms on Earth that thrive in conditions that seem completely uninhabitable. Deep-sea extremophiles live near hydrothermal vents at the bottom of the ocean, where there is no sunlight, intense pressure, and extreme temperatures. Antarctic subglacial microbes survive in lakes buried beneath miles of ice, proving that life can exist in extreme cold. Radiation-resistant bacteria like Deinococcus radiodurans can withstand extreme radiation levels, hinting that life might endure even in harsh cosmic conditions. If Pluto's subsurface ocean is anything like Earth's deep-sea environments, microbial life could exist there, feeding off chemical reactions between rock and water. The big question is whether Pluto has the right ingredients to support such chemical reactions. Scientists can't travel to Pluto just yet, but they have ways of looking for signs of life, biosignatures, from a distance. These are chemical or physical indicators that suggest biological activity. Organic molecules, the building blocks of life, would be a strong sign that something unusual is happening beneath Pluto's ice. Unusual gas emissions, such as methane, could also suggest biological activity, since methane on Earth is often produced by microbes. Chemical imbalances in Pluto's environment could be another clue. Life tends to create distinct chemical patterns that differ from what would happen naturally. If scientists find evidence of strange chemical reactions on Pluto, they might suspect something alive is influencing the environment. The New Horizons spacecraft provided humanity's first close-up look at Pluto in 2015, revolutionizing our understanding of the dwarf planet. But a single flyby wasn't enough. To truly determine if Pluto has a subsurface ocean or even life, a future mission would need to orbit Pluto for long-term study, analyze its thin atmosphere for signs of unusual gases, use radar instruments to penetrate Pluto's ice shell, and look for liquid water beneath the surface, and potentially deploy a lander or ice-penetrating probe to study Pluto's ice and search for organic compounds. NASA has considered potential Pluto orbiter missions, but these are still in early planning stages. A mission would likely take at least 15 years to reach Pluto, making exploration a long-term challenge. However, with new advances in space travel and scientific instruments, the search for life on Pluto could happen within our lifetime. While Pluto is one of the most extreme worlds in the solar system, it also challenges everything we thought we knew about habitability. There's clearly so much here that we have no idea about. The incomplete picture, what New Horizons didn't see. When the New Horizons spacecraft flew past Pluto in July 2015, it provided humanity's first detailed look at the distant world. The mission was a resounding success, revealing an active and geologically diverse planet that defied all expectations. However, the flyby was just that, a single pass lasting only a few hours. While it transmitted breathtaking images and groundbreaking data, it left many questions unanswered. New Horizons captured high-resolution images of only about 40% of Pluto's surface. The rest remains a mystery, hidden in the shadows of space. If Pluto's heart and towering ice mountains were only discovered because of this brief encounter, what might still be lurking on the far side? Could the missing 60% hold even more surprises? Perhaps geological formations stranger than anything yet seen, or evidence of complex processes reshaping Pluto's icy crust. One of the biggest limitations of the New Horizons mission was its inability to orbit Pluto. The spacecraft traveled at nearly 36,000 miles per hour, too fast to slow down and enter orbit. This meant scientists had just one chance to gather as much data as possible. As a result, Pluto's northern hemisphere was imaged in much higher detail than its southern hemisphere, which was in seasonal darkness at the time of the flyby. Large portions of Pluto's terrain were seen only in low resolution, and some areas were completely missed. The spacecraft's instruments could analyze Pluto's thin atmosphere and detect hints of surface composition, but they couldn't provide a long-term study of its weather, geology, or potential underground ocean. Without an orbiter, Pluto remains largely unexplored, with more unknowns than known. The discoveries New Horizons did make have fueled calls for a dedicated Pluto orbiter mission. Many planetary scientists believe Pluto deserves another visit, one that would allow for continuous study rather than a fleeting glance. NASA has considered mission concepts for a Pluto orbiter, but the technical challenges are immense. Unlike Mars or Jupiter's moons, Pluto is an incredibly distant target, sitting roughly 3.7 billion miles from Earth. A spacecraft launched with today's technology would take about 15 years to reach Pluto, and to orbit it, the probe would need an advanced propulsion system or a complex trajectory that would take even longer. Adding to the difficulty, Pluto's weak gravity means an incoming spacecraft would need to slow down significantly to achieve orbit, requiring either a powerful braking system or a complex series of gravitational assists from other planets. Despite these challenges, scientists continue to push for a Pluto orbiter. Proposed designs suggest that a spacecraft could use nuclear power, similar to the Curiosity and Perseverance rovers on Mars, to provide long-term energy for instruments. Once in orbit, it could map Pluto's surface in full detail, studying its shifting ice flows, monitoring its atmosphere over time, and searching for direct evidence of a subsurface ocean. A lander, or ice-penetrating radar, could confirm whether liquid water exists beneath Pluto's frozen crust. Such a mission would be expensive, likely exceeding several $1 billion, but its potential to rewrite what we know about the outer solar system makes it a compelling goal for future exploration. If Pluto has an underground ocean, it leads to an even bigger question. Is it alone? Pluto is just one of many large objects in the Kuiper Belt, a vast region beyond Neptune filled with icy worlds. Some of these objects, like Eris and Makemake, are similar in size to Pluto. If Pluto has maintained liquid water for billions of years, could other Kuiper Belt objects have done the same? The idea that oceans might exist so far from the Sun challenges traditional views of planetary habitability. Until recently, scientists believed that liquid water could only exist on planets close to a heat source. But discoveries on Europa, Enceladus, and now possibly Pluto suggest that internal heating, rather than proximity to the Sun, may be enough to keep water in a liquid state. If this is true, the Kuiper Belt could be filled with hidden oceans, which is a potential region for future astrobiological exploration. The New Horizons mission was a historic milestone, but it was only the first chapter in Pluto's story. The data it sent back led to more questions than answers, leaving scientists eager for another mission to uncover what remains unseen. What this means for the solar system and beyond. For decades, astronomers believed that life could only exist within the Goldilocks zone, the region around a star where conditions allow for liquid water on a planet's surface. Earth, Mars, and possibly Venus in the distant past fit this model. But Pluto challenges that assumption. Sitting 3.7 billion miles from the Sun, Pluto is far outside the traditional habitable zone. Yet, evidence suggests it may harbor a liquid ocean beneath its frozen crust. If Pluto, an icy world at the edge of the solar system, has managed to retain liquid water, then life could survive in far more extreme environments than previously thought. This realization expands the search for habitable worlds beyond Earth-like planets, forcing scientists to rethink where life might exist, not just in our solar system, but in exoplanetary systems as well. One of the leading explanations for Pluto's potential ocean is the hot start theory. Pluto may have formed in a violent collision or from rapid accretion, generating enough internal heat to melt part of its interior. If this was the case, Pluto's underground ocean could have existed for billions of years, sustained by residual heat and radioactive decay in its core. This idea changes how scientists view other icy bodies. If Pluto's internal heat was enough to sustain liquid water for so long, then many other distant worlds could have similar conditions. It leads to the possibility that subsurface oceans could be common in the outer solar system, not just rare anomalies. Many known exoplanets orbit at great distances from their stars, much like Pluto does from the Sun. If Pluto-like worlds in our own solar system can maintain liquid water, then similar exoplanets could as well. The idea that habitable conditions may exist even in cold, distant regions suggests that life beyond Earth might be more common than we ever imagined. Instead of focusing solely on Earth-like planets in habitable zones, scientists may need to broaden their search to include icy exoplanets, rogue planets, and other seemingly inhospitable worlds. Pluto's revelations have reshaped our understanding of planetary habitability. It has shown that liquid water can persist in the most unexpected places, potentially supporting life in ways we never anticipated. If an ocean exists beneath Pluto's surface, how many other hidden oceans might be waiting to be discovered? The future of Pluto exploration. Pluto's surprises have left scientists with more questions than answers, making a return mission an enticing but complex challenge. Unlike New Horizons, which provided only a brief glimpse, a Pluto orbiter would need to stay in orbit, gathering data over months or years. However, sending such a mission is no simple feat. Given Pluto's extreme distance, more than 3.7 billion miles from Earth, reaching it would take over a decade, even with the fastest spacecraft available. Maintaining power over such a long period is another issue. Traditional solar panels wouldn't work efficiently that far from the Sun, meaning a spacecraft would require a nuclear power source, like a radioisotope thermoelectric generator. Engineering a probe capable of lasting for decades in deep space, with minimal human intervention, presents one of the biggest technical challenges of modern planetary exploration. Funding is another major obstacle. A Pluto orbiter is estimated to cost at least $3 billion, which is a significant investment. Critics argue that with so many unexplored worlds closer to Earth, such as Europa or Titan, prioritizing Pluto may not be the best use of resources. However, supporters believe the potential scientific rewards far outweigh the cost. If Pluto harbors a liquid ocean, it could be one of the most intriguing places in the solar system to search for life. Confirming the existence of subsurface water and possibly detecting organic molecules would fundamentally alter our understanding of habitability beyond Earth. A Pluto mission could also answer lingering questions about its geology, atmosphere, and interior structure, filling in the gaps left by New Horizons. Beyond Pluto itself, the Kuiper Belt holds many other mysteries. Objects like Eris, Makemake, and Haumea are Pluto's distant neighbors, yet little is known about them. Some scientists suspect they too could have internal oceans or surprising geological activity. A future mission to Pluto could extend its reach, providing insights into the broader Kuiper Belt and how these distant worlds formed. Understanding Pluto is just the first step in unraveling the secrets of the outer solar system. The discoveries made on Pluto so far suggest that it is far more dynamic than ever imagined. Its potential underground ocean, shifting surface, and unexpected geological activity challenge long-held assumptions about icy worlds. If Pluto, once thought to be a frozen, inactive dwarf planet, has an ocean beneath its crust, then the same could be true for many other objects in the Kuiper Belt. As technology advances and interest in outer solar system exploration grows, a return mission to Pluto may become a reality. Whether in the next few decades or further into the future, Pluto's story is far from over. What do you think? Leave your thoughts in the comments below, and if you liked this video, don't forget to subscribe to our channel. See you in the next one.